So this talk is about entropic independence, which is a notion similar to spectral independence that Zhongchen already talked about. But I'll go from the basics. I won't assume that you know everything, so don't worry about remembering everything. So the talk is based on actually 3 joint works. But the main body of the talk is based on joint works with Rishesh, Fred, Hui, and June. And if there is time, I'll talk about a further follow-up of this line of research on entropic independence that was done with Yang and June. All right. Okay, so Zhongchen has already motivated this very well. So let me go through this very quickly. The problem I'm addressing in this talk is about sampling from combinatorial objects. I've drawn a cartoon on the right. Think of maybe, as just a running example, think of sampling a random spanning tree from a graph. So there are many different ways of doing this. One of the very successful approaches to sampling from large spaces of combinatorial objects is to use local random walks or local Markov chains. So for example, on the right, I have a picture of all spanning trees from some graph, and I've drawn an edge between 2 of them if the difference between them is small. So think of, I'm just removing an edge and adding another edge in order to move from one spanning tree to another. And the type of random walk that I want to use to sample from this large space is just walks on this graph, on this underlying graph. So I start from somewhere, I jump to a random neighbor, and so on. Okay. So it's very easy usually to define these local random walks. The challenging part is knowing how long you have to run them for, how long do you have to jump before the point you're at is nearly, let's say, uniformly at random from the space of all things that you want to be sampling from. So the issue is, what is the mixing time of this walk? And that's the challenging part of usually the analysis, not coming up with the walk. And let me just say that this is one of those subjects for which theory is actually important. The thing is, if I give you like a generic random walk, we don't know of any general purpose technique to measure if the walk mixes in a certain amount of time. So you just have to like have an upper bound on the amount of time that you have to run the walk for, and then when you implement it in practice, just run it for that amount of time. And this greatly motivates a sharp understanding of the mixing time of random walks, because in practice you need such upper bounds. Okay, so in the Markov chain analysis community, there is a phenomenon that happens quite often, which is you have some sort of a Markov chain that can sample from a space of combinatorial objects for you, and you want to analyze its mixing time. So at first, maybe nothing is known. So you have trivial upper bounds that are exponentially large in the parameters that you care about. Then quite often somebody does some spectral analysis of the Markov chain. So they analyze its eigenvalues using some method, and they manage to get some sort of a polynomial upper bound on the mixing time. But oftentimes spectral analysis is not enough, as Zhongchen already mentioned. So somebody else has to come in and do what I call entropic analysis of the Markov chain in order to get a better bound. And oftentimes entropic analysis is enough and gives you an optimal or nearly tight bound on the mixing time. Okay. So this talk is going to be about a technique for automating this middle part, at least in some cases. Okay, so just going from spectral analysis to a nearly tight mixing time. Okay. And the example I'm going to have, the running example I'm going to have throughout the talk is going to be on matroids. So spanning trees are a special case of matroids, but let me just motivate general matroids. So think of a bunch of vectors in some vector space. So here I have 6 host vectors, and a matroid is just a collection of all linear bases you can form from these vectors. So here, out of these 6 vectors, I can construct 8 different linear bases. And the sampling problem I want to solve for these is to sample one of these things uniformly at random, right? Okay. So turns out that for a lot of combinatorial distributions, including matroids, it's useful to think of them as hypergraphs. And what do I mean by that? In my example of matroids, I have n objects, and I want to be selecting subsets of these n objects. For matroids, all of these subsets have the same size. So I view my distribution as being supported on this very important ground set, n choose k. Okay. So combinatorially, you can think of it as a hypergraph, as a weighted hypergraph, where for every element here, I create a hyper edge between the elements of this set. Okay. So this one corresponds to this rank 3 hyper edge. Okay. So many combinatorial distributions, as Dongchen has already shown you, can be translated into a weighted hypergraph, and then the question is, how do you sample from this weighted hypergraph? Okay. So once you have a hypergraph, there are a host of natural random walks that you can use to sample from the hyper edges of this hypergraph. I should also mention that the hypergraphs that we end up with usually have, their hyper edges are super large. So you shouldn't think of the size of the hyper edge as being anything like constant or anything. So for example, exponential in the size of the hyper edges is not enough for us. Okay. Once you have a weighted hypergraph, there are these canonical random walks that you can run on the edges of this hypergraph that can produce samples from you. These are called down-up random walks, and Dongchen has already shown you some of the special cases of this, including Glover dynamics. More generally, if you have any distribution on n choose k, the down-up random walk, the way it works is it has 2 steps. So you start from somewhere in your n choose k ground set. You drop one of the, so let's say I start from here. I drop one of the elements in my set to go to a set of one size smaller. So if I started from here, I go to one of these 3 sets uniformly at random. And the second part of the step is I go back up, and this part I have to do it with probability proportional to the target distribution I want to be sampling from. Okay, so maybe I went in the first half step from here to here. Now from this 2 set, there are exactly 2 sets of one size larger that are supersets of it. So if my distribution was uniform on all of these sets on the top, I would choose one of these 2 uniformly at random, but more generally, you choose one of them with probability proportional to the target distribution that you want to be sampling from. Okay. So this is the type of random walk that I want to be analyzing. And if the distribution that you started from was on a product space, like in Dongchen's talk, this would be exactly equivalent to Glover dynamics. Okay. All right. So let me quickly tell you what we know for matroids. I'll get back to these things. So for matroids, if you run this random walk together with Kui, Cheyenne, and Cynthia, we showed that the mixing time of this random walk is order of k squared time. K is the size of the sets on the top. And this was done, unsurprisingly, using spectral analysis. And then later on, this beautiful work of Cry and Gu and Musa showed that the mixing time can be brought down to nearly linear in K, which is also tight. So this was done using entropic analysis. And let me just quickly say that nearly linear in K is an obvious lower bound because whatever set you start with, you need at least K steps in order to replace all of the vectors in your initial set, because each step only replaces at most one of them, right? So in order to forget where you started from, you need at least K steps, and that's basically the tight running time. Okay. All right. So all right. So let me just remind you a notion that Dongcheng already described in his talk, the notion of spectral independence or high dimensional expansion. So this is the underlying workhorse behind both of these results, but by itself, it only gives you a spectral analysis, which gives you a non-tight mixing time. And I'll show you in the rest of the talk how to translate that into a tight entropic analysis. So what is spectral independence or high dimensional expansion for a distribution? So it's a notion that was initially invented in a context that was very different from things that we study in Markov chain analysis. But if you're dealing with distributions on n choose k, it's very easy to describe. So it's about eigenvalues of a particular matrix that measures correlations in your distribution. So think of your distribution as being on n choose k, and you can form an n by n matrix whose entries are going to be things of this form. The probability that some element j is in my sample, given that I is in my sample, minus the unconditional probability that j is in my sample. Okay. So, so the name spectral independence actually comes from the fact that this is this thing is zero or nearly zero for distributions where different elements look independent or almost independent from each other. And so spectral independence or high dimensional expansion is a way of measuring how close to zero this whole matrix is. So a spectrally independent distribution is one where this matrix, this n by n matrix, has always eigenvalues bounded by some constant. Actually, you need this bound not just for your distribution, but conditionings of your distribution too. But I'll get to that. I'll get to that point later on in the talk. Okay. So the point is, you know, just to have your bearings right. Let me tell you, for matroids, what do we know about this this matrix? For matroids, we actually know this matrix has an eigenvalue bound of 1. So this is always, the eigenvalues of this matrix are going to be between 0 and some large constant generally. But for matroids, that large constant can be further improved to 1. And in general, whenever this is bounded by a constant, it's useful because you can derive very good mixing time bounds on Danoff walks. All right, so I told you about matroids, but really this technique of bounding the eigenvalues of this correlation matrix and using it to analyze Danoff random walks has been done to many other distributions. Zhongchen already mentioned a bunch. But this is a spectral condition, and naturally, the type of result you get from this is also a spectral bound on the eigenvalues of the Danoff random walk. So you could ask, are these bounds that we are getting from this sort of analysis tight or not? For a lot of these, the naive bound that you get is not tight, but there were two works in this series of works that I've listed, and there are many more that I couldn't just list on the slide, that managed to show how to get better and even sometimes tight results on the mixing time of down-up walks just based on that notion of spectral independence. Okay? So I've listed the main two approaches here. So Zhongchen already talked about the left work. And I also mentioned the right work, the work of Krayan, Guo, and Musa. So under two sort of very different assumptions, people managed to get a nearly tight mixing time bound based on some sort of an entropic analysis. So, so the work of Chen, Liu, Vigoda, and later improvements to it, they show that if you have a distribution that's defined on a graphical model, so here the distribution is you have a graph, you have an underlying graph. Each vertex of it is taking values from some domain, and dependencies can or basically like you have this notion of conditional independence, which means that if you condition some of the variables corresponding to vertices in your graph, and if that conditioning separates the graph into two parts, those two parts are conditionally independent of each other. Okay. So, so the work of Chen, Liu, and Vigoda showed that if you can, for your graphical model, if you can show that these assumptions hold, you get a nearly linear mixing time on the down-up walk, which is the same as Glover dynamics here. Okay, so what are these assumptions? The first one is really spectral independence, which I've written as being a good high-dimensional expander. But the other assumptions are conditional independence, which comes from which is another way of saying that the model is graphical. But there are also some crucial assumptions beyond just being graphical. The main one being that the degrees in your underlying graph have to be bounded by a constant. And then the other main assumption is that the marginals of your of each variable in your distribution and all conditionings of your distribution are lower bounded by a constant. So these two conditions are very crucial in the analysis of Chen, Liu, and Vigoda, but somehow in a lot of the applications of this work, they don't seem to be that necessary. And part of the motivation for this work was how do we get rid of these sorts of conditions, and even this one. So okay, so Chen, Liu, Vigoda give you a very general purpose tool to prove nearly linear mixing time bounds, but you know, has a lot of assumptions that don't always seem that necessary. On the other hand, the work of Krayan, Guo, and Musa, it has a similar flavor. It assumes a good high-dimensional expansion and gives you a nearly linear mixing time on the down-up walk. But instead of this list of assumptions, it replaces the bound on the correlation matrix, the spectral independence parameter, by something really strict. So the work of Krayan, Guo, and Musa basically assumes that C is upper bounded by 1. If you remember from this slide. So the work of Krayan, Guo, and Musa only works in the regime where C is bounded by 1. So the natural question here is, what about all of these other models for which we don't have the assumptions of one of these two works? What about high degree graphical models, for example, or what about distributions that don't have this conditional independence assumption? There are lots of these things that I can describe to you. Or, you know, one crucial observation is that both of these works give you a nearly linear bound on the mixing time. And there are a lot of cases where nearly linear is simply just not the answer. So for distributions where nearly linear is not the mixing time, the correct mixing time, there is basically no hope that one of these two works would give you the tight answer. And in this work, we answer all of these cases. Okay, so let me mention, let me state informally what our result is. Our result is assuming that, so we replace basically these assumptions, we remove these assumptions and replace them by something else. So it's not exactly comparable to the first result. So we assume that you have spectral independence for your distribution. So that's standard, but also you have spectral independence if you apply an external field to your distribution. So that's external field is really the key term. And let me define for you what external field is very informally on this slide. I'll define it more formally later on. So external field is this operation that I can pictorially show you on matroids. So conditioning of a distribution is something that Dongchen mentioned, but an external field is a generalization of that operation. So what does external field do? So say I start from a matroid defined by these vectors, and I replace one of the vectors by multiple copies of it. Okay, so maybe I replace this one by 3 vectors on the right, 3 identical vectors, or maybe I even replace this one by 2 identical vectors, right? So morally, what I'm doing is I'm multiplying the weight of all linear bases that contain this vector by 3, and all linear bases that contain this vector by 2. That's an external field. Okay, and you can easily see that this operation obviously preserves being matroid. So if I start from a matroid on the left, I get a matroid on the right. And so naturally, for matroids, if you know that they are a good high dimensional expander, they're automatically a good high dimensional expander under arbitrary external fields too. Okay. So basically, our result subsumes the result of Kraya and Guo and Musa, because for matroids, or generally for distributions where their work applies, we automatically get spectral independence or high dimensional expansion under arbitrary external fields. Okay. All right, so this is the plan for the rest of the talk. I have to quickly tell you a little bit about functional inequalities and the way we analyze Markov chains. Then I'll introduce the notion of entropic independence and how it's different from high dimensional expansion or the eigenvalues of that correlation matrix. And then if there is time, I'll mention one further application beyond just analyzing the mixing time of down blocks. Okay. So let's start with functional inequalities. So the way, or the high dimensional expanders approach to analyzing down walks is through functional inequalities. So what do functional inequalities tell you? So suppose I start from some distribution and I run one step of the down-up walk. So I get a new distribution on my sets, right? So if I started from this deterministic point, now I might be at a random point with this distribution, right? Okay, so functional inequalities tell you that if you keep applying this operator that maps distributions to distributions, the thing on the right converges to the target distribution you want to be sampling from, in this case, uniform on these linear bases. And this measure of convergence is for functional inequalities, you measure this convergence in terms of something called an F divergence generally. So what is an F divergence? So let's say that I want to be sampling from a distribution mu, and I run a Markov chain, maybe the down-up walk, and the distribution of my location at time t is governed by this mu t, right? So what I want to be measuring from is how far away is mu t divided by mu, or the density of mu t with respect to mu, from being the all ones density, right? So pick your favorite convex function f. This is a univariate convex function. And F divergence measures this deviation from 1 based on this quantity. So you compute F of this ratio in expectation and subtract F of the expected ratio, right? So if nu t was an actual distribution, this would be just 1. So you subtract F of 1. Okay. The important thing to note is that if you have a convex function by Jensen's inequality, this is always positive. And if your function is strictly convex, this is 0 if and only if you've already converged to be null. So there are two popular choices for this F. There is the choice of F equals x squared, which I'm gonna casually call as variance, but it's really the chi-squared divergence between mu and mu. And another popular choice is x log x, for which you get the KL divergence between mu t and mu. Okay. So what you want in functional inequalities is to show that the measure that you choose, maybe variance or entropy, contracts over time as you run the Markov chain, right? So contraction of variance is related to the spectral gap or the eigenvalues of the Markov operator. Contraction by some factor is usually called the Poincaré inequality. Similarly, for entropy, you can consider contraction by a constant factor at by some factor by some multiplicative factor at every time, and that sort of contraction is called the modified log subalgebra inequality. Okay. All right, so this is really the type of contraction that I'm talking about. Pick your F from these two choices. And the contraction I want to be having is that if you run one step of the down-up walk, after the down-up walk, my F divergence has shrunk by 1 minus rho factor. So if you have this sort of inequality for down-up walk on your distribution, then a quick calculation shows that the mixing time, at least in F divergence, can be bounded by the F divergence of the start divided by rho. This is because every row iterations, you multiply your F divergence by a constant factor. So it takes log of this many of those super iterations to for this to become super negligible, right? So something very small. Okay, so let's do some back of the envelope calculations. So in a distribution defined on n choose k, the starting distribution, it's actually somewhat important how to choose it, but you can often choose it to be at least as good as an average starting point. So let's say for matroids, the starting distribution is going to have weight 1 on one set, but the distribution I want to be sampling from is going to be uniform over all of these sets, and there are roughly n to the k many of them, right? So the initial variance for starting from a single set is going to be upper bounded by polynomial in n to the k, right? So if I have some contraction for variance, the mixing time, I can bound it by log of n to the k divided by the contraction factor for variance, right? And so you can bound this by k times log n divided by the contraction factor for variance. On the other hand, if you have this for entropy, you get a much better rate, and the reason for it is I can bound the initial KL divergence between my starting distribution and mu by log of n to the k. So this means that I get a log instead of a single log in the numerator. And that translates to log k plus log n divided by rho of entropy. And as Zongchen already hinted at, this is really the bane of all of the problems. This is why spectral analysis is usually not tight. This factor of k in a lot of applications you can get rid of, including in the case of matroids. This is the thing that gives you k squared instead of k. I should also mention that in many cases, including the case of matroids, you can also get rid of this log n, but that's a story for another time. We mostly don't care about this additional log. Okay, so that's great motivation for studying contraction in entropy, but entropy contraction is also connected to a lot of other things studied in theoretical computer science. Including things like hypercontractivity, concentration of let's say Lipschitz functions and things like that. And for that, you can read this beautiful survey by Paco and Tita. Okay. So my goal is somebody has come and done the hard work for me. Somebody has done some spectral analysis for me. Can I just use that to get the same result for entropy contraction and get a better running time? So of course, this is impossible in general. And a quick example is, let's say, if you're analyzing a random walk on a constant degree expander, for these random walks, variance contracts by a constant factor every time. So raw variance is omega-1. But mixing time of a random walk on a constant degree graph can be upper bounded, can be lower bounded by log of the size of the graph. On the other hand, if you had a row of entropy being bounded by constant, instead of this log, you would get log, which is clearly wrong. You need these many steps in order to move from any point to any other point in a constant degree expander. So at least for expanders, these things are separated, right? Entropy contraction and variance contraction. Okay, so you clearly need some other assumptions, and that's the reason we introduce external fields and these things. Okay. So now let me move. Let me move to entropic independence. So as I said, we want to analyze the down-up walk, and we want to show that some measure of distance to our target distribution, some F divergence, contracts by a multiplicative factor of 1 minus rho every time. This is usually done by breaking up the down-up walk into two steps, the down step and the up step. Okay, so if you remember the down-up walk, it first removed an element and then added back an element. So this is the first part is the down step, and the second part is the up step. So if I show that the down step already contracts my F divergence by some multiplicative factor, that's enough for me, because neither of these steps can actually increase the F divergence, so including the up step. So if I show the first part contracts by 1 minus rho, the second part cannot increase that. So overall, I get my contraction. Okay. So the challenging part really now has come down to how do you show that the down step contracts your favorite measure of F divergence, and this is done by some technology that started from the literature on high-dimensional expanders, but Ronen is going to tell you some more advanced and maybe simpler to a probabilist machinery for these things. So okay, so what I want is to analyze some sort of a down operator like this, right? So I have some measure on my sets of size 3 here, and my down operator maps them to distributions on sets of size 2. So this phenomenon, which people in high-dimensional expanders literature call local to global, tells you that in order to analyze this, it's enough to analyze a much simpler down operator. So this one goes from sets of size k to sets of size k minus 1. Instead, analyze the down operator that maps things from sets of size k to sets of size 1. Okay. It's the same sort of down operator. So given a set of size k, I choose one element of it uniformly at random, right? And that gives me a distribution on n elements. Okay. So what Alev Lau and subsequent works, which are too numerous to mention on this slide, show is that if you can show that the k-to-1 down operator has contraction of the form this thing, some constant divided by k, then you get a so this is absolutely not an operator that you want to be algorithmically running. This is just for analysis. So this thing that you can't run can be translated to something that you can run, but with a much worse contraction parameter, right? So if you can show that the k-to-1 operator contracts by a factor of c over k, then the k to k minus a constant down operator contracts by a factor of 1 minus 1 over k to the c, right? And you can already say that this is very sensitive to this constant c. Okay. So okay, so knowing this, you can now consider two different notions, one coming from variance, one coming from entropy. So spectral independence, which I showed you at the beginning of the slides, basically becomes equivalent to showing that the k-to-1 down operator contracts variance by a factor of c over k. And entropic independence, analogously, becomes equivalent to showing that entropy contracts by a factor of c over k, right? Okay. All right. So I already told you that spectral independence becomes equivalent to the notion that I told you in the beginning, and here is a cartoon of why this is true. So variance contraction of the k-to-1 down operator becomes basically equivalent to some bounds on the eigenvalues of the up operator combined with the down operator, right? So usually we are studying down up walks. This is an up down walk. So I flipped the two operators. So this is moving from sets of size 1 to sets of size k, and from sets of size k back to sets of size 1, right? And the reason for this equivalence is that these two operators are adjoint in some appropriately normed spaces. Okay. And okay, so this random walk, which moves between the n elements by going from one element to set of size k and then back down, it's basically equivalent to this other random walk, which moves from sets of singletons to sets of size 2 and then back to sets of size 1. These are two random walks which are basically equivalent to each other. One of them is just a little bit lazier than the other one. So this one is formally like a convex combination of this and the identity matrix. Okay, and then you can again map this back to contraction of something like the 2-to-1 down operator, right? And this is really now you can begin to see why this is all like related to just a simple n by n matrix. So if I have a measure k, if I have a measure on k size sets, if I map it down to two size sets by the down operator, now that distribution on n choose 2 is really capturing everything I want to know about this operator, right? So that's why you can basically analyze spectral independence through just the eigenvalues of a simple n by n matrix. So this whole scheme breaks down for entropy. So for entropy, you can't do any of these. You can't basically do these up-down arrows. So you can't translate dk-to-1 to d2-to-1. Another way of saying that is entropy contraction of the dk-to-1 operator is not really a property of an n by n matrix. Okay. All right, but entropic independence has something else going for it. So here I've written what we want to prove: entropic independence on the top. We want to show that the k-to-1 down operator contracts entropy by a factor of c over k. And let me go quickly because I'm running out of time. So if you just stare at this inequality that we want to prove, there are, there is a quantifier here for all distributions new. You want to show that the down operator contracts entropy, but really you just have to look at only some special distributions new in order to check this inequality. And the reason for this is if I look at all distributions new which have the same new decay to 1. So this is marginals of my distribution new, right? So for all distributions new which have the same marginals, I have the left-hand side, and I can look at what distribution new minimizes the right-hand side for them, right? So in order to prove this sort of inequality, I just have to look at the minimizing distributions new given a set of margins, right? And this is really the greatest thing going on for entropic independence. Distributions new which minimize the KL divergence subject to given marginals are distributions given by an external field over your original distribution. So more formally, you have your distribution mu, you assign a multiplier for each of the n elements, and then you get this skewed distribution mu, where I'm multiplying different sets by these different multipliers, right? Which is an external field. Okay. All right. And because I'm running out of time, let me not dwell on this too much. You can show this through some convex. This was known in for a long time, used by many great works, including a work of Nishit and Mohit. But really, the way you show this is through some convex program that tries to minimize entropy given a set of marginals, and the dual of that convex program gives you these external field multipliers, right? So you can formally show this is the minimum KL divergence. It's a result of a convex program over these external field CIs. Okay. All right. So one thing that I want you to just briefly look at on this slide is that the objective of this convex program is something like the partition function of the external field applied to your distribution divided by some other factors, right? So this is what people usually call a generating polynomial of your distribution. So this is the sum over all sets of mu s times the product of zi's. This is the normalizing factor in this definition. Okay? And okay, so this generating polynomial, so it's enough for me to basically upper bound this generating polynomial in order to show entropic independence. If I can upper bound this, then that gives me whatever the optimum of the upper bound is in this convex program gives me a way to check that this inequality holds. Okay. All right. So in the so this is going to be my last slide, and then I'm gonna quickly go to the conclusion. So this is really the way spectral independence and entropic independence compare. So when you look at this generating polynomial, in order to show entropic independence for it, you just have to upper bound it by some other function of zi's. So in particular, if I upper bound it by something like some linear function of zi's, maybe something like this to the power k, that's really showing entropic independence with a factor of c equals 1. Similar upper bounds give you entropic independence with different c's. Okay? So it's a global property of your generating polynomial, entropic independence. So in order to show entropic independence, you just have to upper bound your polynomial by something like this. Pictorially, it looks like this. So you have your generating polynomial, and I've drawn the level sets of it. So the points where my generating polynomial gives me a value bigger than 1. And you just have to show that this level set is lower bounded by a linear tangent and at the point all ones. So this is what entropic independence really needs. Spectral independence is a property of just marginals and pairwise correlations in my distribution. So the moral of the story is that it can be written as a condition on just the gradient and the Hessian of my distribution, which pictorially, after simplifying all of the math, looks like this. If I look at the same level set, if locally this level set is convex around the point all ones, then I have spectral independence. Okay. And really, our main theorem is just this simple observation that if you have the left property, not just at the all ones point, but at all of the points in the positive orthant, you get the right property. Another way of saying that is that if you have local convexity of this level set at every point, then you can bound the level set by a tangent at any point you want. Okay. All right, and since I've run out of time, I apologize. I'll just conclude here and open up for questions. So really, the result that I showed you was that if you have spectral independence, if somebody has done the hard work for you, but you can show it for all external fields applied to your distribution, you automatically can boost it up to entropic independence, which gives you a better mixing time. I didn't have time to go over applications, but in many cases, this is giving you the nearly tight mixing time. All right, thank you.